right. Well, I think I've been through about 3 or 4 of the sessions here since yesterday, and probably we're going to see a lot of repeat data. So we'll burn through some of those slides, but make sure, stop me if you want me to focus on any of the particular topics. The other thing, come to realize, is some of the contradicting information from one speaker to another. And it reminds me of the old adage, opinions are like noses. Everybody has one. So now we're going to see another version of what my opinion is for thermal management, and we're going to specify for LED applications. My name is Yash, Sutariya. I work with Saturn Electronics. We're a rigid bareboard manufacturer. I also own Saturn Flex Systems, where they're a rigid flex supplier, and we're going to see different applications using both rigid as well as flex technologies for potential LED solutions. The main purpose of my presentation is defining your needs. I've seen prints from all types of companies, ranging from startups to multi-billion-dollar corporations when it comes to LED applications, and the one thing that everyone has in common for the most part is the way they specify their fab notes. And what I see a lack of is specifying actual critical needs and an abundance of basically specs that I consider either dangerous or potentially creating waste. So, the end result of, a fab note being the proper way should be not only for you defining your needs, but you should have real concrete benefits, shorter lead times, lower costs, and higher reliability in your product. So we've seen this chart many times, but basically, let's talk about metal core boards. You've got your metal substrate, whether it be copper, aluminum, stainless, brass, the dielectric layer, and the copper circuitry. The focus will be basically on that dielectric layer itself. That's where you're spending your money. So, moving forward, maybe we'll get a little bit interactive. Maybe show of hands. How do you currently specify your materials? Raise your hand if you're calling out actual part numbers of materials. For example, like a Berquist MP3 or a Laird 1KA. Looking good so far. Are you specifying thicknesses of dielectric? Anyone? Maybe we'll skip all this hand raising. TGs, TDs? Simply saying metal core? Or are you actually calling out electrical insulation resistance or thermal conductivity, thermal resistance? All right, well, let's go through the survey answers. It was pretty interesting. We gave this survey during a webinar about a year ago on thermal management materials. We had about 120 people represented online. I think it was at least 2/3 were calling out by a specific material manufacturer. Now, what's the drawback? Well, obviously, it locks you into a particular product that is produced by a single manufacturer. Of course, your risks. Pricing. You're at the mercy of their pricing. You're at the mercy of their lead times, and you're basically locking yourself into a point in time. You're not allowing your product to take advantage of new materials that may become developed over time that either have lower costs or increased performance, which is kind of a big drawback. It kind of makes you think, who calls out a brand name for a standard FR4 on your rigid boards? Practically no one. With the lead-free, some people are still tending to do that, even though we see more of a movement towards TDs and TGs. So I really think that the LED market will transition to calling out more performance-based metrics instead of either brand names or what have you, as people start learning more about it. I think right now the market is moving so fast, it's really not much time to put thought into, what do I really want to use in my product. Thickness of dielectric, TG, TD. These are all good things to call out. They may have an impact on reliability, but they don't fully address your needs, which are actually moving heat from your component. So again, you're not addressing thermal conductivity, you're not addressing electrical insulation resistance, and you're not addressing the actual type of the dielectric that you're looking for. And then I still see this, which is kind of amazing to me. They say, oh, just make it metal core. No specs whatsoever. It's very dangerous because you don't know what you're going to get. You might get the best product. You might get something that does nothing for you from a thermal performance perspective. So again, you're just not addressing anything whatsoever. So as Napoleon Dynamite says, you are a rock star if you are calling out actual insulation resistance and thermal conductivity values. These are what you're looking for, so why not specify them? So it all comes down to your needs. You have needs when it comes to thermal management. Put them in the notes. So, what are these needs? And it was amazing, the difference between survey answers. Like 2/3 were calling out by name, but 90%, chose A, or A and B, which is your actual performance metrics. So that's kind of what we're going to delve into with this presentation. So first of all, these are high volume products typically, LED applications. Cost is a major, major concern. And your number one cost component of an LED board, which is your typical metal core single layer, is we see the most volume of, is that tiny thin little piece of dielectric in between your copper circuitry and your metal base. And that deserves to have focus put on it. So essentially, it's your insulator for shorting out to your base, and it's your conduit for transferring heat. If you take a look at your construction, it's all available on the market. You've got aluminum, you've got copper foil. And if you look at the cost of some of these 18 by 24 panels, do the math. You might be talking about $8 to $10 for an 062 18 by 24 aluminum. Copper foil is 80 cents. What are you paying for your raw material? $45, $55, $60. You're ranging for that tiny thin piece of dielectric, probably $30 to $40 on the multi-purpose ones. Standard FR4, to put it in perspective, it might be $3 to $5. So think about how much value is in that dielectric that you're paying for when you're specifying a particular product. And think about what you can do to reduce that cost. It's your easiest target. So number one, it's the most effective way to reduce cost is to introduce competition. A lot of people hate me right now. We've got the market leaders, Laird and Bergquist. It's good material. They're good companies. But they're not the only game in town. You've got a few representatives of material manufacturers in the audience today that have come out with their own thermally conductive materials. You've got, Ventec, iTech is here, Inselectro, as well as DuPont. I don't think I see William here, but they're all here. Ask them, these questions. You can get information out of them because you're buying their material. So the main thing is that last point, future innovators. I'm a bare board manufacturer. People come to see me to sell material. I swear I've not had more visits than in the last 3 months from people pushing new product. And it could be very well fantastic stuff. It could just be an equivalent. It doesn't matter. The main thing is there's people entering the market. By speccing out a brand name, you're not allowing to take advantage of that. Also, you're not securing your supply chain. If you find that they're equivalent material manufacturers, allow the use of all of them. That way, if someone wants to quote a 12-week lead time, someone else might come in at 3. You're really just ensuring your supply chain. So I'm not going to spend time on all of these, but basically definitions and applications. You've seen it on previous slides today as well as yesterday. But thermal transfer, electrical insulation, that's really your performance characteristics. So, thermal resistance, thermal conductivity, there are two primary call-outs. Let's just start burning through slides because we've seen this. The main thing is a lot of the information for use in a calculation is available on data sheets, not just in the bare board material, but also in the components that you're looking to draw the heat away from. Essentially, I just threw out this LED component, and I think they call out you're dissipating 3 watts You've got your thermal resistance of your junction, and you've got your junction temperature. These are pieces of critical information that you could use to make a pointed calculation for what you need out of a material performance. So there's the first half of the calculation is the smell test. Can I even dissipate as many watts as required in my package? So what we've got are your inputs. You've got your 3 watts of heat that you're looking to dissipate. You've got your the resistance of the junction. I think it's 10 Kelvin. As well as now you've got your stack up. So I just threw in a thermally conductive material. You've got your the heat sink itself. I think we use aluminum in this calculation. And then your tin, the thermal interface material. So essentially what we've done is, drawn out the math on this, and this is a model that was created for me by Clemens Lassance. He was a professor emeritus at Philips Corporation. His focus was on thermal dissipation from the Lumileds product line. So some people call him the godfather of thermal management. I just call him a really smart guy. But very simple calculation once you have the results. The math behind it's pretty intricate, but what we've done is said, well, you've got 11.6 watts, Kelvin of resistance, and the maximum dissipation that you're going to have is 9 watts. So 9 is greater than 3. You're looking good so far. The package is working. You don't need to look at a different type of LED for your product. So now we're going to go into the heatsink package. What's the actual, the end dissipator of heat? So what we've done here is we've said, okay, well, our heatsink, we're going to extend the area. Typically you'll have fins on your heatsink, so now your surface area is increased. And we said, throw a number out there. It's a factor of 20, perhaps. As well as what's the convection method. Here, let's choose just natural convection. It's out in open air. So you're going to get, perhaps 10 watts per meter Kelvin. And so now what we've got is we have a required total maximum thermal resistance of 35 Kelvin and, of 21 Kelvin, but our package is generating 35 watts of 35 Kelvin of thermal resistance. It's no go. It's not going to work. And here we figured it out on paper before you've actually gone through prototype phase and things like that. So what we've got to do is revise our package to effectively cool the base of that LED to dissipate as much heat as you need to. So let's change it to just forced convection. I don't want to redesign anything. My materials are good, my design is good, but just changing your method of convection dramatically reduces your thermal resistance of the entire package. So great, we're down to 21. It's under 35. Our job is done, right? Not really, because we also have to think about cost. What's the best way to reduce cost in this package? So right now, we've got a lot of room to move. We're talking about a difference of 15 Kelvin. So let's take another look back at that stack up and see, where is your opportunity? Going back to the previous slide, number one opportunity for cost saving is your dielectric, period. So I just threw in from the data sheets the thermal conductivity value of FR4, 0.4 watts per meter Kelvin. And it works. It seems to work in this calculation. Now remember, we're talking strictly thermal conductivity. When you talk about calculations for heat spreading, they're much more intricate. Those are where, everyone has slightly different models. So I'm not saying that it's a catch-all solution, but, heck, it's worth a try. You could take off $30 out of the cost of an 18 by 24 panel. Divide it out. You might get 6 pieces on a panel. That's math that I can't do very quickly. $5 apart. I mean, they put it in volume. You're talking about saving, hundreds of thousands, sometimes millions of dollars, right to the bottom line, without affecting performance, without redoing your design, and using, commonly available materials. You're basically, making your supply chain better, and it was just ease of just substituting materials. So, again, don't take the calculations in a vacuum. Heat spreading has a different dynamic associated with it, but it's worth a try. Again, plug in the thermal conductivity values, see if they work, and then take a look at the heat spreading properties. You're already getting the heat down to your final heat sink. It probably looks worthwhile. So your other cost drivers, it's not proper to ignore them. We've got aluminum and copper are the most common choices for the metal substrate. You're talking about what, 3x difference in cost. The metals themselves are very thermally conductive. And I think Intellectual pointed out yesterday, while there's about 2.5x more performance in terms of copper versus aluminum, the aluminum is so much more thermally conductive than the package above it, it really doesn't behoove you to go to the copper and spend the money in many cases. So the other thing is, you could also use that calculator to reduce the size of your final heat sink. Again, a cost saver without affecting the final performance. The other thing is breaking out of the box. I've seen design after design coming in. Oh, single-sided circuitry, give me some Laird or Bergquist or Ventec or what have you. But, there's different ways to skin a cat. I've just getting into the flex business, you're looking at some of the values of the DuPont materials. I think they were talking about the AP and the FR, Kapton materials. They naturally come in thin dielectrics, 1 mil, 2 mil, 3 mil, very commonly used. And as you can see from yesterday's calculations, thermal conductivity, it's a number to look at. However, when you take into account the thickness, you're calculating your thermal resistance. That's the critical number, that, at least in my opinion. And when you have thin materials, you have a lot lower thermal resistance, even with a material that has a lower thermal conductivity value. So, hell, just slap on a 2-layer flex, use some vias to make a thermal connection to the ground plane on layer 2, maybe some thermal grease, put it right onto your final heat sink. Eliminate the metal substrate alone. A couple people will probably kidnap me at the end of the day in this audience, but it's an option. Like the presentation before us. We were talking about using expensive methods to plug vias and then plate over them. Add a little copper. It's so much more conductive than any dielectric out there. You could achieve the same thing. Just dissipate your heat directly with your vias. The other thing is, forget about the thermally conductive material. Typically, your LED has is a metal base that's not electrically connected to any of the other circuitry. Maybe you just use some no-flow pre-preg. Pre-route it, bond it straight to your aluminum. That way your LED sits right on top of your final heat sink or the metal substrate. It's not that expensive, especially considering you're already throwing out, $30, $40, $50 per 18 by 24 sheet. Routing FR4 doesn't cost that much, and you'll achieve actually a better performance out of it. I think the main point is it's always good to think differently. Sometimes, we see ideas that probably, I don't know what they're thinking. They say, I can draw it on the screen, so you should be able to build it. The rule doesn't always apply. But sometimes you might hit on a moneymaker. There are designs out there that we've seen that achieve greater thermal performance without using fancy materials. You just have to try. In electrical insulation, there's so many ways. I'm not even going to get into it, but because it's been covered quite a few times. But I think they made a great point yesterday. Consider your UL needs. I've been in a couple of situations when they're doing their UL roll-up the material they called out didn't meet their voltage insulation requirements for UL. So again, be cognizant of that. Check into all of these factors before doing your build. So these are just, the test conditions, methodologies for testing the electrical properties of that material. This is one that I don't think there's enough focus on, reliability of the material. IPC is generally who we rely on for setting up standards. What properties does the material have to fit in category A, B, or C? And I think they're working on that, and I'm pretty excited for when they do come out with it, because it'll allow some more standardization within this portion of the industry. And as well as I hope they develop some life cycle testing. What makes a material reliable? Just because I'm putting dielectric on a metal doesn't mean one material is the same as the next. You've got adhesion issues, you've got voltage breakdown issues over time, as was previously mentioned, and it'd be great to see some standardization. But until that's done, it's always good for the OEM to come up with their own methods, and maybe sometimes they become adopted as the status quo for the industry. So again, what should your fab notes look like? I'm a big proponent of fab notes being the right way, because I get burned as a PCB fabricator when they're written a little bit improperly. So again, the purpose. What do you deem to be most important? What are those product characteristics? So you're going to have your copper weight, you're going to have your metal type. And here's where I see a lot of people lacking. But these are great numbers to put in there, the thermal conductivity. Truly, you should probably focus just on the thermal resistance, because that's a real performance indicator, as well as electrical insulation, and maybe even throw in some pre-approved materials. That gives the board house guidance. They might already be using and have one of these or two of these as a preferred supplier, or they can at least consult with their own preferred supplier and say, hey, do you have something that's equivalent or better than that I could submit to the customer for approval? And all the customer gets is the benefit of quicker lead times and lower costs, two things that we're always striving to achieve. So again, your benefits, pretty simple. It's not rocket science. And as we start collecting information, we find out there's quite a few material options. And so, you can go to the website, it's an interactive chart, plug in what you think is most important, and you'll get a smaller list of materials that meet your needs. This is just a snapshot. This thing is growing every day. I think one thing that's very important, a little bit on the fly here, the intellectual presentation, where they had their testing values. B stage versus C stage. C stage, their numbers with C stage, which is the cured material, the pressed material, came out to be much lower. I think a third of the conductivity value as the published data. And as you do more research, and I implore every OEM to ask, their chosen material vendor, what is your data based on? Because in questioning, I found that sometimes some people are using B stage. And for those of you who don't know the vernacular, B stage is uncured material. As an OEM who buys the final product, you will never receive a PCB that has B stage material in it. It will fall apart. You receive C stage. So shouldn't you be calculating all your performance, your thermal stack up, if you will, using C stage values? And if they're not available out there, then they really should be. So I'll probably modify this chart to have a second column, B stage and C stage values. I think that was huge. It's a big thing that they discovered. And I think you probably got their contact information. I would probably stay in touch with them as they start, furthering along with their tests, evaluating, here are differences between B stage and C stage. I think that is it. And I stayed within my 30. So anybody have any questions for me? All right then. Thank you.
Presentation.